Welcome back to our series on applied regression analysis. I'm Mark Ledbetter. This is lecture video 31. We're in chapter 9, part 3. We're in multiple regression, and we're talking about how to do different hypothesis tests in this chapter. So I'd like to remind you of what we did in the last video. We talked about the partial F-test, and this is where we looked at the partitions of the regression sum of squares, SSR. We partitioned it, and we used conditional probability. So the first variable, whatever variable we choose to put in the model first, then we have sum of squares x. And then we calculate, we basically figure out whether we have to run another model or whether the computer does it for us. The conditional sum of squares, that is the sum of squares regression, that is the additional sum of squares that are added to the regression sum of squares for x2 after x1 is already in the model. So this is the additional sum of squares that are the sum of squares that are explained, the additional variation explained by adding x2 into the model when we already have x1 in the model. So this is the additional amount. And the same thing here, the sum of squares x3 given x1 and x2 is the additional sum of squares that or variation that's explained by adding x3 into the model when x1 and x2 are already in the model. Okay, so this is the additional sum of squares that is explained or that helps predict y. And so we'll define a full model as one that contains all p variables, initial variables, and then our additional variable here. Okay, and the reduced model only contains the first p variables, excuse me. Okay, and so then our F-test, our partial F-test here, was x star given x1 to xp is the sum of squares of x star given that x1 to xp is already in the model divided by the sum of the mean square error of x1 to xp and x bar. Now I want x star. Now I want to point out that I don't like the notation. I should have noticed it in the previous video, but I just remembered this is actually the ms of x star given x1 to xp because it's divided by 1, which is the degrees of freedom, the extra degrees of freedom of this. Okay, so we have a mean square here, but it's the same as the sum of squares because we're dividing by 1, all right? So we've talked about the partial test last time. Now we're going to talk about the multiple partial F-test. So let's see what we're getting ourselves into. So this is an extension of the partial F-test. We can consider addition of 2 or more independent variables when other variables are already in the model. So last time we only considered adding one variable at a time, and we only looked at the individual contribution and whether adding one variable was significant. Now we're going to talk about adding 2 or more variables at the same time and see whether or not they're significant. Okay? So that's the multiple part of this partial F-test. So, for example, we may add x1, x2, or x1, x3, or x2, x3, okay? So, and let's see. It says, when a set of variables has a common trait, we may want to consider them together. We can also consider a collection of two-way product terms. Okay, so not x1 and x2. This is x1 times x2. This is x1 times x3, or x2 times x3. And we'll talk about what this means later on, but we can consider that. And by considering a group of variables together, we can reduce the number of tests to be performed in the variable setting. And we'll see later on in the course why this is important, because it inflates our type 1 error. The more tests we run, the more error is introduced into the model. Okay, so the null hypothesis. Suppose we want to test whether adding k additional variables say x1 star to xk star, significantly improves our ability to predict y, given that we already have x1 to xp variables in the model. And so how can we state this null hypothesis? So the null hypothesis can be said H naught beta 1 star to beta is equal to beta 2 star is equal to ... beta k star is equal to 0 in the full model versus HA. Again, anytime you do a hypothesis test, I want you writing the full test in there, the null and the alternative. I want you to know, make sure that you know what the alternative is. And this would be that beta star I not equal to 0 for I in 1 to k. So for some I, or for, I should say, at least, let me rewrite this. For at least one I in 1 to k. Okay. Now, so in the full model, and then they list out the full model. So please remember, always write your model that you're talking about. So here's the procedure. We're going to define the extra sum of squares as follows. So the sum of squares x1 star to xk star given x1 to xp is the sum of squares regression with all of them in there minus the sum of squares regression with only x1 to xp. And remember last time we talked about how this is different, how the sum of squares with x1 to xp is bigger because less variables are in the model. That makes the error bigger, minus the sum of squares error of all of them in the model. Okay? And so the F statistic is here. It's given by this. So this is our test statistic. Okay, so test statistic, step 2 in our hypothesis test. And that is F of x1 star to xk star given x1 to xp. And that's going to be, you'll notice that now, because we have more than one, we have to divide by k. So this is the mean square of the sum of squares, but there's not really a name for it, and so that's why I guess we leave it this way. So sum of squares of x1 star to xk star given x1 to xp, which is either one of these values, which is the same value, divided by k, so the degrees of freedom of adding k variables, which is k. So we have a degree of freedom for every variable that's added. So we have that k, all divided by MSE of the full model. So by doing that, we want to have the full MSE because that's the case, we're dividing by that because that's the case where we have included all of the variables in the model. And here we do have all of the variables in the model. If you remember from last time, we had the table and we had source and we had x1 and then we had x1 given x2, x3 given x1, x2. And I don't remember the numbers, but and then we had error, okay, and I remember it was like 195 point something, and I remember this one was 0.24, and I forget what the others were, but this, when we do this, when we're here, then we have added all 3 variables into the model in that case, and so this error that was down here goes with this, these two go together. And so that's what, but what we're doing in effect here is we're taking both of these and adding them together, okay? We're taking both of those and adding them together, and that is going up here. And then we still divide by this. And so that is an F test. And the difference is now the degrees of freedom in the numerator are no longer 1, it's k. So I cannot make a t-test that's alternative with this one because I don't have 1 as the degrees of freedom in the numerator. Okay, so there is no alternate t-test here. Okay, we have to use an f-test for the multiple partial test here. Okay, so here's my table. I'm so sorry. So I'd forgotten that I put it in here. I'm glad I did. So let's explain this a little bit better, the test statistic. Okay, so I have, in this case, let's see, do we work that out? We do. Okay, so we're going to work this out. So let's take a look. We have f of age, and so what we're doing is we're going to say age and age squared. So this was x1, x2, comma, given x, or x2, x3, I'm sorry. So we're given x1. So x1's already in the model, and this is x2, and this is x3. So that's what we're doing. And so we look at the sum of squares of age and age squared, so x2 and x3, given x1, and we're dividing by 2 because there's 2 of them. So this value here, divided by 2, is going to be these 2 values added together. So that's going to be 104. Let's see if I'm right. 104, 14. And then the MSE is going to be the 24.4 here. Okay? And so, did I do that right? Let's see. So this is this extra sum of squares. And, okay, so they did a more convoluted equation here to go back to their definitions, and you're welcome to follow that. But let's see, I've got, so what do they have here? They have 588. Oh, yeah, so they have 588 plus 588.92 plus 103.90 plus 0.24, because what they're doing is they're getting this value here, and then they're subtracting this value here. But I just want to point out that you can get the same value, that this and this cancel out. So you end up with this, okay, which is what I put here. So there's 2 different ways to think about this or to get this number. And you need to know both because you may not have a nice table like this given. So you need to be able to get it from multiple regression tables, okay? So what they're doing here is they're saying this is the sum of squares regression when we have all 3 in the model. If you remember, I wrote out a source and then SSR with x1, x2, x3, and that had, let's see, it was, I add these 3 together, 5.92 plus 103.9 plus 0.24. So this was 693.06, and so not SSR, but regression, because the SS is here, degrees of freedom, and this was 3, and then error or residual was, let's see, so there's 11, so that was 8, and it was, how much? 195.19. And then the total is 888.25. Remember, I wrote out 3 different regression models. One that had just x1, another that had x1 and x2, and then this third one that has x1, x2, x3. And so this value here is this, is what's right here, which is this one, okay? And then SSR with just HGT, with just height, is x1, and that is this value here, the regression model with that, okay? And so if I wrote out the ANOVA table, okay, if I wrote out the ANOVA table for just x1, then I'd have source, and I'd say regression, x1, error, total, and here regression I'd have 1 degrees of freedom, here I'd have 11, and so here for the error I'd have the difference, which is 10, okay? And then for SS, I would have 588.92, and then this is still 888.25, and so the difference between those two, 888.25 minus 588.92, and that's how the computer calculates it, by the way. It calculates the sum of squares regression, and then the difference between it and the total is the error, so 299.33. Okay? All right. So that was the one with just one, and then we did, and as we added another one, when we added two, x1 and x2 together, we had this, and we only had 195.43 as our sum of squares error when we had two in the model. Okay? So, back to what I was saying. I know this is confusing, but I hope you'll pause the video and think through what I'm saying and try to get this understood. I do warn you that you have to really think about this to get this. So 103.9 plus 0.24 is the way that I did it. And that was, so I said 103.9 plus 0.24 divided by 2 is, I can get this quantity, well, this quantity here directly from this table by adding, wow, that's messy, by adding these two, the extra for those two together, and then we have 24.4 on the bottom. When I do this, I get 103.9 plus 0.24 is 104.14 divided by 2 over 24.4. And so divided by 2 and then divided by 24.4, and I get 2.134, etc. Okay? And so this is, so we can round to 2.13. And the critical value, we need to look at K. So let's see if we can find this in our F table. Hopefully I have an F table. Tables. F table, good. Take a minute to load, because I had to use Cam Scanner to take pictures because they don't have an electronic version of this book as far as I can tell. Okay, and so let's come back over to here, and so K was 2 in this case, 2, because we were adding two variables. So I've got 2, and then n, see, remember this is n minus 1 degrees of freedom in the total, so n was 12. So I've got 2 and then 12, n minus p minus k. P was 1, that's what was already in the model, and 2 that I was trying to add, and then minus 1 here. And so that's 2, 12 minus 1 minus 2 minus 1, so minus 4 is 8. And then 1 minus alpha, which is 0.05, so 0.95. So this is the critical value that I'm looking for in my table, F2895. So 0.95, so this is the upper 2.5%. I don't want that, I want the upper 5%. So let's see if I can find, that's 1%, 0.5%. Let's see, 0.1%. So did I not include everything? 1%. Oh, it's up here. Good. Whew. Upper 5%. There we go. Upper 5%. I have 2 degrees of freedom in the numerator. This is the numerator. This is the denominator. So it was 2 and 8. And so I'm going to zoom in here so I can see. And sure enough, 4.46 is the critical value. And so I'm going to erase all this mess so that we can see. And so what we do is we say the rejection region. I always want you to write out the rejection region or the rejection criteria or the critical region. Any one of those words is fine. Is F greater than F, K, n minus p minus k minus 1 minus alpha, and then fill in the values. So here we had 2.13, so this was 2.13 greater than, and we found 4.46 in the table. Whoops. And this is not true. So do not reject, whoops, H naught. And then our conclusion is, let me remind you, there does not exist sufficient evidence to support the claim. Now, HA is that that X1, that adding age and age squared to the model, regression model, sorry, containing height, no, not WT, H, is it, yeah, HT, whatever, height, HGT, I forget what they use, anyway. So there does not exist sufficient evidence to support the claim that adding age and age squared to the regression model containing height improves the prediction of weight. Yeah. At a 95% confidence level using a simple random sample of n equals 12. All right, so that's our conclusion statement. Sorry, it's messy, but you have it written elsewhere. Okay, and so they give a little explanation of what we did over there. So you have that to read if you. I'll pause here so you can read that if you need to. Okay, so here is what I was saying earlier. If we have two ANOVA tables, we can find this directly from the table. Okay, so here we're looking for this SSR of height, age, and age squared. So here I have 693.06, okay? And so that is SSR of, I'm going to say X1, X2, X3 is equal to 693.06. And then we have SSR of X1, which is our reduced, is equal to 588.92. And then we subtract these. And that gives us the 104.14. And that was exactly what we had. What I had given you earlier was 103.9 plus 0.24. So that's 103.9 plus 0.24 is 104.14. Okay? So if you have the two ANOVA tables, you have to do it this way to get that additional, and it would be the difference between those two. All right. So I hope that helped explain this multiple partial F-test. So the difference is that we're adding more than one variable at a time to a model that already has one or more variables in it. And we want to test whether the whole group of variables we want to add as a group, are they significant? Now, if you remember our result here that we said, last time we said that adding x2 to the model, the probability was between 0.05 and 0.10. So really, it was borderline significant, right? But, and the F value was 4.78. So But here, our F value was 2.13 and it was nowhere close to 4.46. Why don't we go to our F table and see if we can find out the p-value, kind of closely, the p-value for adding both of them. What happened here is when we added just one, it was borderline significant. But remember that X3 had a p-value of 0.923 and the F statistics 0.01. It's almost completely worthless as far as predicting the weight. Okay, so h squared is almost worthless in predicting the square. That's one way to say it, but not very professionally or technically. Okay, so don't repeat that. So let's see if we can find the 2.13 under 2 and 8 degrees of freedom in the table. Oops, there we go. So here, this was 5%, and 2 and 8 was 4.4, and so do I have 10%? Yep, so 2 upper 10%, so I've got 2 and 8, and so 3.11, and so we don't have, do we have any? Oh, we do, good. So this is the upper 25%. 2, 8. So the p-value is going to be between 0.25 and 0.1. And let's see, so this value is 3.11, and this value is 1.66, and 2.13 is between there, and without a table, I wouldn't want to guess how close it is to which one. So this is 0.25 to 0.1, I'm using this, okay? I'm using these values up here as the upper value. So, so the P here is between 0.1 and 0.25, okay? And it's real close to the middle between those two. And so, so it's definitely not significant. Grouping both of them together, the X3 is hurting the chances of X2 to get added into the model. So together they are less significant than just adding X2 by itself. Okay, so when we grouped it together, now if one of the variables is a really poor fit, it may cause us to reject putting all of the variables in because we're only considering them as a group under this multiple partial f-test. So that is the drawback or disadvantage of using this method. All right, please don't forget to scan your lecture notes by midnight of the date listed in the course calendar. You definitely want to update your formula sheet. If you have questions, by all means, come to the virtual office hours. If you just can't do that, then email me a picture of the problem and a picture of your work so far, and maybe I'll be able to help you easily through email that way. I hope you'll take care of yourself, stay safe, and we will see you next time.